Students, welcome to lecture number 5 of the course on material informatics. So, in the last 4 lectures, we deliberated on mostly regression. Obviously, I provided you some basic concepts of MI or material informatics, but the technique on which we focused our discussion is the regression. And today we will finish the last part of the regression and we will start a new topic on probability and classification. And this is something new, many of you may not know that there is a technique called naive Bayes, which is based on the Bayesian probability theory, and we are going to talk about that. So, in the introductory concepts, we have already discussed about statistics and regression. Today we are going to start probability and classification, and then again we will discuss these aspects later on, how to use these techniques. So, as you know, regression is a very technique which is used by every modeler, and because it is very easy to handle and also it has many aspects which is good for machine learning techniques. Hence, we have spent quite a lot of time in describing what is regression, what are the different aspects of regression, right. So, as you know, regression is basically finding correlation between the dependent variables and the independent variable. You may have one dependent variable or you may have more than one independent variables, and how the dependent variable is correlated with the independent variables. That is the main aspects of regression. We talked about it, we do not want to go back into details of that. So, basically we like to find a functional relationship between the dependent and the independent variable, and the easiest one, the simplest one, the relationship is basically a straight line passing to the origin of the plot. That is basically equal to y equal to b1x, where b1 is the slope of the line. So, now you can also complicate it, you can always have a straight line which is intercept on the y axis, that is given by b0 here, and b1 is again the slope of the line. So, therefore, the relationship becomes y equal to b0 plus b1 multiplied by x, where x is your independent variable and y is your dependent variable. So, one can obviously go higher level of relationships, that is polynomial one, and common polynomial relationships will have many terms, and obviously it can have powers which is equal to x to the power m, where m can be any value. So, the simplest one is basically y equal to b0 plus b1x plus b2x square. So, the x square term is added with a coefficient bu2 in order to take care of the binomial, in order to take care of the polynomial nature of the relationship. So, you can also add b3 x to the power cube, b4 x to the power 4. So, what I mean to say is that one can always write a relationship like this, b0 plus b1 x plus b2 x square plus b3 x to the power cube plus b4 x to the power 4 and so on. Okay. So, that is the common polynomial relationship possible between an independent variable x and dependent variable y. So, many of these tests and curves basically follow such a kind of relationship. All of you know that the stress is given by k into f10 to the power n, right. So, where n is basically an exponent and it can have value more than 1, it can also have value less than 1, right. So, that is what it is. So, therefore, these kind of relationships must be represented by polynomial type of relationships. So, other than that, you can also have trigonometric functions coming into picture. You can have exponential terms coming into picture, logarithmic term comes into picture, or many things possible in nonlinear relationships possible, right. We do not want to deliver each of these aspects, but it is possible. So, when you have data, you can actually fit your data using this kind of nonlinear relationships also. These are the different combinatorial models, like you can have inverse relationship x between x and y, parabolic one or hyperbolic one, exponential one, logarithmic one, different kinds of curvilinear model representations are possible. Am I clear? So, before you go into probability classifications, let me iterate that regression is a very good model. It is a fundamental essential method in machine learning, but many advanced machine learning techniques use these relationships or the regression models. So, therefore, regression is considers a very fundamental model in this case, but as any other method, regression has its own problems, right. It has its own problems. The major problem is regression is overfitting of data. So, whenever you are having lots of data, you will try to fit with different kinds of models, linear or nonlinear models, and chances are there you may land up in overfitting the data. And machine learning overfitting is not a good, because it can predict with a very high accuracy if it is overfitted. So, therefore, we must avoid overfitting. Please understand that. So, therefore, there are few challenges when you use this regression model. First important challenge is there are too many variables. As you have seen, the thing I have given relationship, this one, you can see that there are too many B's here, B0, B1, B2, B3, B4 and so on to be determined, right. Although you have an independent variable x is 1, but you can also have many independent variable possible, input variable possible x, p, q, many others which are governing the value of p. Very simple one is the stress of any material depends on strain, depends on temperature, depends on strain rate, right. So, therefore, you can see the straightforward relationship between stress and these variables will be a very complicated one. So, when you try to fit such a kind of model, such a kind of things where there are many variables, what you land up is create a big computational burden, and also it requires sometimes big data to obtain a satisfactory relationships, which you may not have in material science. You may not have always the big data, huge amount of data available with you. So, therefore, there is a problem of using the regression model. That is the first important problems you will face. So, therefore, the second problem is essential problem is that these models are not built on strong scientific backgrounds or foundations, and hence there is always problem of overfitting, as I discussed with you. How to take care of that? So, there are two ways of taking care of overfitting, correct. Basically, overfitting can be taken care of by adding a penalty term in the model, okay, which can take care of overfitting, that you have understood, right. A penalty term to be added to the objective functions of the regression models, and penalty term is also called sometime regularization term, okay, regularization term. It regulate the value of or the model very nicely, right. And we always use k-fold validation in these cases in order to take care of overfitting. And what is k-fold validations? Basically, it is very simple, and in the extreme case, k-fold variation is basically nothing but you split the data into n and n minus 1, sorry, you split the data into k folds or k minus 1 folds and form the cost correlation between them. That is the idea. So, that with that you can actually take care of many of these overfitting problems, but nonetheless adding a penalty term is very important. So, yesterday I talked in the last lecture, actually I talked about penalty term related to lasso, right. Lasso I talked about it. So, let me tell you what is that, and you know that lasso is what. Again, let me write you it. List, L stands for list, absolute, A stands for absolute, shrinkage, very interesting, right, and selection operator. That is the full form of lasso. This is also known as L1, because that is the penalty term we had. I do not want to discuss in detail about that. What do you do? To the objective functions of the regression, we add the term which is like this: j goes to 1 to n wj, or rather write bj less than equal to less than actually t. So, what we are doing? We are saying summation of all the values of b. B's are basically what? They are the coefficients of the regression model. Summation of all the coefficients, when you take a mod value, it must be less than a preset value. That preset value you can always provide to the model. Okay. Remember, this t is a preset value. So, t preset value, you can decide yourself that preset value when you model it, depending on the character of the data. So, this is the term, or this is what is the penalty term we add, right, in lasso model. So, what you do? What is the equation? So, let me write that equation for you, so that you don't forget it again. And so, therefore, the values of b, the optimized values of b for lasso is given by minimization of, you know that, right? We minimize the value, take the first derivative or first order derivatives of the, of the basically difference of the function which you have derived. What is that function called? That function called least square. Let me tell you, I told you that function name, right? Should not forget it. So, that is called basically residual sum of square, or sometimes called objective functions. So, that has to be minimized with respect to the coefficients p. So, only way to minimize is simply taking the first order derivatives of that function with respect to different b's and make it 0. So, that means this argument w and sum it over I is equal to 1 to n, and then the difference, right, yi minus w0, sorry, b0, these are nothing but variables. So, it is better to write w, because in the last lecture also I used w, right, then you do not confuse much, right. Remember that yi, I said yi is equal to w0 plus sum it over j equal to 1 to n wi wj xj, right, that is a linear model, right. So, wj coming from there. So, yi minus wj minus sum of what? J going to 1 to n wj x ij, right, square. That is your least square aspects, right, or what do you call, that is your residual sum of square. Residual sum, we have, this is my level, this is actually the predicted value, and this is your fitted value. So, difference between these two is taking the square of that is basically called residual sum of square. Okay. And we with this we add a additional term, that is, this has to be minimized with respect to. So, we add a additional term, and let me explain again, j going to 1 to n, correct, that is all. This is how we can predict the value of b, actually all the b's. Remember, this lambda is Lagrange, don't mistake, Lagrange multiplier. Okay, that is the way. If you want to optimize a function subject to certain condition, we have to use Lagrange multipliers. Okay, please look at books where it will be given. This is a concept of constrained optimization. That is maximization minimization problem. this requires to multiply the Lagrange multiplier with the constraint we are putting in. So, that is what is the lasso is. So, what is then Ridge? Okay? Ridge uses L2 regularization term. Remember, here you are using L1 regularization term. This is your regularization term. So, in case of Ridge regression, what do you do? Very simple. So, I am not discussing details of other parts of that. Ridge regression uses a penalty function which is basically like this. Ridge uses a penalty function that is called, we call it L2 regularization, and the penalty term which is used is like this, j 1 to n w j square is less than equal to t. So, what is the difference between these two? In the case of lasso, we are taking the summation of w's or absolute values of w's, sum it over, and we are saying this must be equal to less than a p set value, that is equal to t. But in Ridge, we are using a square term of w, remember this square term of wj, and we are saying that must be less than equal to a p set value t. This is what is your penalty or regularization term, remember this. So, this then has to be added with the function or objective function. So, what you do? What you do that? Will we add that with term with this? So, therefore, what you do is, so w Ridge, in order to save the space, so I simply write w's, this will be w here, w Ridge, optimized values of w by Ridge. Okay. The moment I put a tilde, I am saying optimum values of w. Okay. That is equal to, again same thing, a argument w, sum it over I 1 to n, remember this I 1 to n, then yi minus w0 minus j going to 1 to n wj x ij whole square plus lambda j equal to 1 to n wj square. So, this is, by this optimization you can find out the different values of w. So, hence you can see the difference between this and this. In the first case we are using this as a penalty function or a regularization term, okay, or in case of Ridge we are using this as a penalty term or regularization term, right. Please remember that. That is the main idea. Main concept of these is basically your main concept is basically the using this penalty terms. Okay, that is the main idea. So, now as you understand, our objective function I am not describing again, but I can write it down here for you. Our objective function was what? Objective function is the residual sum of square, right. I can write down objective function which is nothing but residual sum of square. Remember that? Go back to my lecture number 3. So, RSS residual sum of square is which will allow you to determine both W0 and other W's, right. That is nothing but sum it over I is equal to 1 to n yi minus W0 minus, if you are not using, if you are using many W's, so j 1 to n Wj x ij square. remember the square. This is why the least square technique comes into picture. So, this is your residual sum of square, and now we actually optimize, we basically find out the optimum values of W0 and all the other W's, simply taking the first order derivative of this with respect to W0 and other W's. We write down all the first order derivatives, correct. So, very simple is basically if you want to remove the sum. So, simple case is what? Simple case is very simple case is this, I going to 1 to n yi, remember I have done all this mathematics, w 1 x whole square, right. So, now we can basically take this is simple case RSS. So, first you can take del RSS by del W0, that is equal to 0, correct. You can do yourself that mathematics, and del RSS by W del W1, that is equal to 0. Okay. So, therefore, by putting these first order derivatives, you can find out the value of both W0 and W1 here. So, similarly, when you have many W terms, you can actually take derivatives of each of these W's with respect to the RSS with respect to each of the W's and put it 0. That is what is the concept of minimization, minimizing the RSS. So, you can minimize this function simply by taking first derivatives with respect to W0 and W's other W's and put it 0. Okay, that is the basic concept of regression. But if these terms we add, this requires you to find out the value of lambda, and that can be done. Okay, that is not a very difficult task, because you can also do the similar things and find out the value of lambda. Remember, if you do not know, you can ask the TS, they will be able to explain you, otherwise I can also explain you later on. So, I hope you understand the meaning of this, both the lasso is first one, ridge is second one, regression. Okay. So, these are part of regression, remember that. These are widely used in machine learning models, and you must know what is you are doing when you are using some model. In Python, you can simply call back these functions, okay, but it does not tell you how does it operate. So, here I am describing you how does it operate and how we can find out or optimize values of W's in this kind of situations. So, remember that the LR, linear regression, and nonlinear regression in LR, these two things are widely used, and other than that we can use lasso or ridge. Okay. So, only technique which we will be talking about a bit later is what is called the other regression technique, which we will talk little later, okay, much later, not now, if at all time permits. But fundamentally this all concludes your discussions on regression analysis. Okay, we will not get back into regression later on, maybe logistic regression, that is what I was not able to recollect. Logistic regression, remember that, logistics regression, that is what we will discuss later part. Okay. So, let me just now go back into some aspect of classification, just introduce. Classification is what? It is a task of classifying objects or things in different subcategories, right. That is what we do in classification, that is what we do. It is basically a supervised machine learning technique in which we use level data for training. And since I told you this is a process of categorization of the data or objects into different predetermined classes. So, therefore, we need to know the features or attributes to classify. We should know that. You must be thinking how it is done. Okay, we will come back, we will show you in a moment's time. So, main objective in classification machine learning model is what? Is to build a model that can accurately assign different levels or categories to any new observations. Correct. For example, if a classification model is trained on a data set of image level either as a dog or cat, and then we use that model to predict a new image which is belonging to either dog or cat, it must be able to do that based on color, texture, features, shapes. We know that dogs and cats look differently, we human all know that. But if you want to test a model, machine learning model by using these images, this is what you should do. First you should train the model based on the images which are labeled, and after that you can feed a new image and ask the model to determine which class this image belongs to, whether it belongs to dog or cat. That is the prime example. By the way, supervised learning is basically what you use an input variable and output variable, and both are known to you. The values of both are known to you. Okay, we call it independent variable or levels, we call it independent variable or response. I go back, I discuss about it, and goal is always to approximate the mapping function, so that you can have a new, whenever a new input data or new independent variable data, you can predict what will be the output or level. Okay. So, let me stop here and we will come back to this classification problem in the next part of the lecture in a detailed way.